Okay, so we left off last Friday with taking a look at geometric series, and I want to recap what we did and then move forward. So we took an nth term, an nth partial sum of a geometric series. So first term is A, and then to get to each next term, we multiply by R over over and over again. And then we cut it off at the nth term, where this is n equals 1 term. We multiplied both sides by R, and then we subtracted the two equations to get on the left side of the equation that subtraction, and on the right side, we got a whole bunch of cancellation. Ah, everybody, oh, whoopsies. Hold on. There we go. And everything in between, gone. And we are left with A minus A times R to the n. And then isolating S sub n got us this formula. Now, the infinite geometric series and I'm having to put n minus 1 because I'm starting at n equals 1. The sum of this infinite series is equal to the limit as n approaches infinity of this formula. And then I'm going to go over to what the textbook wrote up to save us a little bit of time with that limit as n approaches infinity. And the first thing it's looking at is just this piece right here. What is that if R is between -1 and +1? This right here is saying the limit as n approaches infinity of R to the n is equal to 0 if R is a number between -1 and +1. And I'm hoping that you can think about that and it makes sense that if you multiply over and over again by a number who is positive or negative, but the absolute value of it is between 0 and 1. If you just look at a positive number and you keep multiplying by a number between 0 and 1, you're making it smaller and cutting it up into tiny little pieces. If it's a negative number, then you're first adding you're adding a term that has been chopped up. Then you're subtracting a term that's chopped up even further, and then you're adding a term that's chopped up even more. And so you're continuing to add something that if you keep cutting it, it's going to head towards 0. And that gives us, this middle part is a little bit confusing to read from the textbook. Realize what it's trying to say is this subtraction sign is that subtraction sign. And then it took the R to the n and factored that out. So this is coming from this 1 being distributed, and then this term is coming from that R being pulled out and left with a 1 there. Ultimately, here's a formula. It's really nice and simple to use. But that's only if R is between -1 and +1. Now, it turns out, and I'm going to show you a little bit, that if you have a geometric series, it is convergent if the absolute value of R is less than 1. But if the absolute value of r is greater than or equal to 1, it will diverge. Now, how do you know if you're dealing with a geometric series? You're dealing with a geometric series, and actually I want to go to some examples before that. You know you're dealing with the geometric series, first of all, if they tell you, but you can also look at, take the second term with its sign, divide it by the first term, then take the third term, divide it by the second term. Anytime you take a term and you divide it by its previous term, you should get the same exact number every single time. And what number is that for this particular example? What is the r on this example? And always be careful of those darn little negative signs poking around. So negative 2/3, and you can get to that either by thinking about what am I multiply 5 by to get that, or you can literally do the division. And come up with your r. Now, because that r is between 0 and 1, you know that you have a converging geometric series. In the future, you're going to be given series either written in this manner, or it could be written as a formula in sigma, which I'll show in a second. And you're going to have to just determine if it converges or diverges. Rarely are you actually going to find what it converges to. But the geometric series is a very clean series that you can actually figure out the infinite sum with a simple little formula. Now, if you are just asked, does it converge or diverge on a test, I'm going to want you to explain what test you use to determine that. And so if it's geometric, all I need you to do is tell me what the r is, and then tell me whether it's a converge or diverge and the test that is being used. That's all you're going to need to say with the geometric series. Now, if you're asked to find the sum, then you're just going to do a quick extra bit of what's the first term? 5. What is the r? Negative 2/3. And then have a joyous time simplifying. 1 plus 2/3 is going to be 5/3. And then voila, the actual infinite sum is 3. Now, the book provided a really nice picture, a graph picture of this geometric series that I want to share with you. And I want to clarify that on the x-axis you have n. However, we only have dots because this is not a continuous function. This is a discrete function where we have, when n is equal to 1, all we have this is the sum of the first term, which is 5. Then when n is equal to 2, it's the sum of the first term and the second term. And I want you to see an interesting pattern. When n equals 3, when I add 3 terms together, when n equals 4, And do you see what's happening here? Do you see the pattern? And I want to point out that we found the sum to be 3. What do you notice is happening with the nth partial sums as we go along? Oh. I understand now what that movement was. Unfortunately, when I'm presenting, I can't actually see all of you, at least not on the school computer. And what I'm going to do is I'm going to just draw some connecting lines that aren't actually there, but just so you see that this is going up and down, up and down. And do you see that it's going bigger than 3, smaller than 3, bigger than 3, smaller than 3? And that's actually going to continue doing that forever. Bigger, smaller, bigger, smaller, bigger, smaller. And while it's doing that, it's getting closer and closer to 3 every single time it gets closer. If you look at a graph of the plotted points of the nth partial sum, you will be getting an answer if you have a horizontal asymptote. Do you see what I'm saying on that? This is horizontally asymptoting to 3. And that is a way to discover that the infinite sum is heading to 3. Okay, then I want to look at another one before I go back and talk about an understanding of why the geometric series diverges for the other numbers. Look at that formula. In the future, you're going to need to look at that formula and quickly identify it as geometric series. So here's what you need to notice. The variable of sigma, if it is only located in an exponent with bases that are real numbers, you have a geometric series. Then the biggest thing you need to do is find R. R determines whether it converges or diverges. And some of you are going to find it quickly. Some of you, it's going to take a little bit longer. That's okay. Whatever you need to do to find it, you don't have to show me how you find the R. This one is tricky. And what I'm going to do is I'm going to rewrite this formula. And I'm going to make the base 3 go to the denominator, and that changes the sign, so it's now n minus 1 instead of 1 minus n. And the temptation is to look at that and say, it looks like R is 2/3. But do you see the little thing in there that's actually going, they don't see me. Who's hiding or trying to hide? Yep, that exponent is 2n, not n. When you're identifying R from a formula, you want to make sure that the exponent is not, where you see that n, that the n is not multiplied by a number. Adding or subtracting a number isn't changing R. That will change the first term, but it will not change the R when you look at subtracting 1 from 3. Because all that's doing, you can multiply the top and the bottom of the fraction by 3, and then you can see exactly that 3 is who is to the n power. That's -1 is not affecting the r, it's affecting the first term. But 2 to the 2n, take a look at what I just wrote and remember your exponent rules. 2 to the 2n is 2 squared to the n. 2 squared to the n is 4 to the n. Know that you do not have to go through manipulating this formula to determine the r. I'm showing you how you can go about manipulating it, because what you're going to finally notice is maybe a constant multiple that's sticking out. But other than that, you have some number to the power of n. That number is r. So if you can work your formula to have just n as an exponent, look at the base, that's r. This r is larger than 1, so this diverges. All I need you to say for a problem like this is r, and it diverges by the geometric series test. Or a lot of times people just say geometric series. Was that a hand? Yeah.
So Miss Blanchard, with the original equation that we found, when you're trying to find like the sigma, isn't it AR to the n minus 1? So why are you finding the n exponent to the n minus 1?
Good question. This is more a technicality than anything, and not to get hung up on. Right now they're using n equals 1. Soon they're going to use n equals 0. And when they start using n equals 0, you can start writing it nicer without that -1. And it's just an issue of what is your starting n. And it's important that you see that that -1 doesn't affect the r. And that both of these are meaning exactly the same thing. The only reason it has an exponent of n minus 1 is because it is specifically saying this is the first term, and if you're starting at 1, then you have to wait one round, before you start multiplying by r. So that's a very good question. And that's all you have to say, is just what is r, and then mention that it's a geometric series, diverge or converge, you're done with that. Now I want you to know what we're heading into. We are heading into a big giant, does it converge, does it diverge, does it converge, does it diverge? The reason that you're going to see in the end, the reason why we're going through all of this is because when we have our Taylor series, Maclaurin series, power series, those are polynomials. And they have a variable which we are not having right now. But do you remember that when you graphed some of these, that the function was only mimicked for a certain distance from the center, and then it just couldn't mimic it anymore. But if you remember the sine graph, it really nicely followed it way, way out. We need to know the domain of this function. When x is put into the mix, we have a function. Right now, we are dealing with infinite series being equal to a single number. We have an infinite series of constants that we're adding together, and those constants follow a particular pattern. When we get to the point of going back to power series, we're going to need to know what values of x is this function valid for. We always want to know domain of a function. We need to know what are we working with, what can we put in. All of this converge diverge is so that we can determine later, well, I mean, it's not the only reason, but we can later determine the domain of those power series we were looking at. Although they call it interval of convergence, but it's exactly the same thing as what a domain is for a function. Now, when you're finding domain, let me throw an example of something you know. Let's say I give you a function, let's make it square root x minus 1. The domain of this function is 1 to infinity. Do you realize that by putting the domain down, I was only looking at what can I plug into x to make a real number? I wasn't finding the real numbers. I wasn't finding the values of g of x. I was just wanting to know what x values can I put in to make this come out real. That's what converge diverge is needing to do. If you plug a number into the x, you get an infinite series of constants. And if for that particular x, you have an infinite series that converges, that x is part of the domain. If it diverges, that x is not part of the domain. And so that is the big step that this is heading toward. However, in and of itself, without heading over to power series, this is math to be looked at on its own as well. That's not its only purpose, but that's the main purpose that we are heading to. You will be asked lots of questions on the AP test about series of constants and whether it converges or diverges. Now, I want to spend a moment making sure that you understand or that you have made some sense of why a geometric series is going to diverge if your r is absolute value greater than or equal to 1. So what I've got here is an example of r being a positive number. And I want you to just logically think about the fact that you are literally adding. You are adding all of these terms together. If you're dealing with an r that is 4/3, it's not very much bigger than 1. But this number is going to grow. The bigger n is, the bigger that 4/3 to the n is going to be. And it is itself heading to infinity. So I want to make sure that it makes sense to you that having an r that is larger than 1 is definitely going to diverge. Now, how about r being a negative number less than -1? we need to take a quick look at this. If I'm multiplying by a negative number, then that means that I'm going to go back and forth between adding and subtracting. When we went back and forth with adding and subtracting with the example right here, we were dealing with an r whose absolute value was less than 1. By having an absolute value less than 1, the amount that you had to add or subtract to get to the next term is shrinking. When you multiply by a number between 0 and 1, that's what it does. It shrinks down to 0. But if your r is bigger than 1, I mean, absolute value bigger than 1, and you're dealing with a negative number, what is it doing? And yes, I see it. I'm looking at chat. It's going back and forth between negative infinities. It's actually going to do the opposite of what we were seeing there. So I'm going to do a quick picture draw. So I had the series starting at 1. So when n equals 1, we were here. Then we were adding to 1 when my r is negative 2. Then I'm subtracting 2 to get to the next term. And so there's my next term. Then I'm adding 4. And you know what? To make this long story shorter, let me draw another picture and microscope it a little and go, it's going to go dink, dink. Well, not quite that, but it's going to get wider. Because you're continually going further from the previous term to get to the next one. But we need to take a good look at 1 and negative 1. So I'm just going to pick a starting number, let's say 5. If my r is 1, then the next term I add is going to be 5. And so is the next term, and so is the next term. And I'm going to continue to add 5 over and over and over. Can you see that if r is 1, adding 5 an infinite number of times is not going to create a real number? That's heading to infinity. It will diverge. But I really want to talk about negative 1. This is important. Let's say I start with 5 again. If I multiply by negative 1, I get negative 5. Multiply by negative 1 again, I'm going to add 5. Multiply by negative 1 again, I'm going to subtract 5. Then I'm going to add 5. And I'm going to continue this process. So what I want you to realize is, in this case, you are dealing with the first term is 5. The second term is 0 for s sub n, I mean. So my s sub 1 is 5, my s sub 2 is 0. Then my s sub 3 goes back to 5. So if I'm looking at the sum, what is happening here? That's a problem for S sub n. It's oscillating. And I want to be careful because you saw a moment ago an oscillation that headed to a number. So there's a very important difference between, where did that picture go? There's a big difference between oscillating toward a single number. If you're oscillating toward a single number, then you're getting closer to it, but you're continuing to go past it. But this situation is not oscillating toward one particular, I'm going to say y value, because you're used to thinking of the vertical as being the y-axis. We are not heading to one particular S sub n. That means that this limit does not exist due to oscillation. But oscillation alone doesn't cause the limit to exist. It's the fact that it's not oscillating toward one number. So not oscillating to one number. And therefore you get diverge. And I feel that I should warn you because I've had people bring it up that if you search the internet, you can find some interesting things about how this series is equal to a real number. But what I want you to understand is the only way that that works is to go outside of the real number system. So if you find some video that tells you that, and I guess from what I understand, it comes from string theory. String theory has weird things happen. We are beyond the real number system. If you find a video that talks about this oscillating series being equal to a particular number, understand it's because we have to go outside of the real number system. Now I have to warn people about that video because it confuses them. Because it makes a great argument, but it goes away from real numbers. Okay, now the first set of your homework problems look like this. And you're going to be doing the odd problems. You are coming into this knowing you have a geometric series. You're determining converge or diverge, and if it converges, you're going to find its sum. And so you've got it in a variety of ways. Remember, the biggest thing is find R. And once you find R, the only other thing you need to know is the first term. And then if R is absolute value less than 1. I'm going to now head over to a next idea. And I'm starting right here. This is a theorem, and the textbook has a proof for it, but I want you to just take some time to think logically about this statement. And also make sure that you understand there's a big difference between the terms themselves versus the nth partial sum. If I look at the sequence of just the terms, then I'm getting first term, comma, second term, comma, third term, comma, nth term, comma. But the sum that is the nth partial sum is first just A1, but then it's A1 plus A2. And then it's A1 plus A2 plus A3. So I want to make sure that you're very, very clear just how different these two are. To say that just the term itself is heading to 0 is basically saying if I'm adding a bunch of these, and now I'm just going to put down like AR. I shouldn't use an R. I just realized I'll put A sub K for some other place, and then A sub K plus 1, A sub K plus 2. And this just keeps going and going and going. How on earth am I going to be able to have the sum approach a real number if the terms that I continue to add forever are not near 0? How can I possibly get an infinite sum that is a real number if I don't eventually wind up adding a very, very small number? And that goes back a little bit to the picture of this. In order to get a horizontal asymptote of 3, I had to continue to add smaller amounts. If I had not been able to continue to add smaller amounts, I would get an oscillation. Where did I put the other one? I will get an oscillation that does not head to one number. Or even crazier, just heads toward infinity. Oscillating or not, this multiplication by the negative 4/3, if it was just times positive 4/3, the sum would be heading to infinity and going up even faster than this one is. It would not horizontally asymptote. So this is a very, very, very important theorem, but it's also important to become very, very clear about what it is saying and what it is not saying. So, are any of you familiar with logic statements, if P then Q? It's like it is a fun little branch of math. I love it. Super, super fun. So if you're familiar with it, you might be familiar with a couple of words that I'm going to bring up. One of those words is converse. Anyone know what converse means in a logical if P then Q? Why does everyone say it's a shoe? Oh my goodness. Okay. The converse statement is if Q, then P. And a lot of people make mistakes in math by assuming that a converse statement is true. So this statement is saying, if you know that an infinite series, and let me emphasize infinite series, if you know it's convergent, then the formula creating the individual terms must be heading to 0. That's the if and the then. So what is the converse statement?
The limit is n approaches, like it's kind of a switching them, right?
Mm-hmm.
If it's greater than the infinity,
Mm-hmm.
it's kind of different.
Right. And this is a nice little warning that your textbook gives you. If you find out, oh wait, hold on. Let me not go there yet. The converse is, if the limit as n approaches infinity of the term itself is heading to 0, does that mean that the infinite series will converge? And for this to be a true statement, it's not that it does, it must converge. Is that enough to say that it must converge, just that its final term is heading to 0? Correct, you have no idea. You really don't. And this is not necessarily true. Necessarily. I had to sound it out. This is not necessarily true. It's very important in math that you understand that when you're given a theorem, it's an if-then statement. A converse of that statement is never automatically true. And oftentimes, it's sometimes true and sometimes not true. So never trust a converse statement to be true. But I will tell you, if the converse is true, mathematicians like to write the phrase if and only if, which they shortcut by if. So if a theorem uses the phrase if and only if, then it's giving you an if-then statement that is true, and the reversal is also true. But now I'm going to introduce you to another word that's really important, the contrapositive. Positive. The contrapositive puts in front of the statements P and Q the word not on the converse. So the contrapositive is if not Q, then not P. And let's take a quick look at this statement. What is the contrapositive of this statement? So I want you to think about that. What is the contrapositive of this statement? And the contrapositive swaps the if-then but nots them. So the contrapositive is if the limit as n approaches infinity of the formula creating the terms is not 0, then the infinite sum is not convergent. And I want you to think, does that sound like it is restating this theorem? So the theorem said if your series is convergent, then you must be heading to 0 for the terms you are adding on. You must be. So if the terms aren't heading to 0, does that mean that it cannot converge? And if you think about it a while, you will realize that the contrapositive has the same truth value of the initial statement. They really mean the same thing. The contrapositive of a true statement is always true. And what that means is, if what you're writing down is a true statement and you write its contrapositive, it is also true. However, if you write down a statement that is definitely a falsehood, like, oh, I got a good one. If the district says that we're going to reopen, then we're going to reopen. There's a false statement. The contrapositive is also a false statement. So that's what I mean by the same truth value. So what you need to know is the contrapositive of theorem 6 is theorem 7, and that is a second test that you now have under your belt. This is referred to as the divergence test, the test for divergence, the nth term test for divergence. It goes by several names because it is that important. If you get that the limit is not equal to 0 or does not exist, you cannot have a converging series. Your series is divergent. But what you have to be careful of is accidentally thinking that the converse statement works, because it does not necessarily work. If you solve this limit and you get 0, this test means nothing to you. This test is only able to conclude divergent. It is only able to make that conclusion. Now, let me tell you how I picture this test. So I picture this as, you know how like you see in shows or movies a line going into a club, and then there's the person at the front door deciding, okay, you're good enough, you can go in, or no. Okay, that's the divergence test. So now I want you to picture a bunch of sigmas with infinity on top, all lined up, waiting to be inspected to see if they can go in, if they're good enough to go into the club. Now, I warn you, though, inside this club are a whole bunch of other tests just waiting to nitpick at the sigma. But they don't want to waste their time. So they need to have this doorman or woman, they need to have this door person ready to say, hey, your final term isn't heading to 0. Get out. You're just go. Why are you wasting our time? And unfortunately, people forget about this test and go and search in the harder to use tests and go, oh no, I can't find a test. I'm lost. I don't know how to determine it. And I call that having club converge missing its door person. The door person is supposed to stop you from getting into a harder technique or getting lost because none of the techniques are working because we didn't need a technique for that because it's blowing up. There's no reason for an extra test for something that blows up to infinity. And you might wander around not knowing what test is going to work. Don't forget the person at the door. Because we often will enter the world of the tests that determine if they're able to go into the full club converge. They have to be inspected by a bunch of tests. And if you go in and you get lost, don't forget to ask yourself, was the door person paying attention? Or did they just let everyone in line in? So here's an example. Just look at that beautiful formula. Do you feel like the answer just pops out? Does the answer pop out to you at this point with the amount of math that you've had now? What is the answer to the limit as n approaches infinity of the formula for the term alone? Yep. And you have been working with this ever since you learned about rational functions with a polynomial over a polynomial. If the degrees of the polynomial on top and bottom match, then the answer to the limit are those leading coefficients. If the degree on top is smaller than the degree on the bottom, the answer is 0. If the degree on top is bigger than the degree on the bottom, then you're heading to infinity, and that means that limit doesn't exist, and get out of here, you're a joke, you're blowing up. And by blowing up, I mean heading to infinity. So what you're going to write on a test is that you found this limit and that the answer was not 0. Then the only thing you have to say is that this diverges by the divergence test. And you're done. These tests are theorems. You don't have to prove the theorem when you're taking a test in this class. The theorems are giving you the answer. All you have to do is show that you met the conditions of that theorem. And then you can state the name of it and say, this theorem tells me diverge. Done. Now, in your homework, I have this section of problems. And I have given you certain problems, but not other problems. Some of the series in here are geometric. Some of the series in here are not geometric. Some of them you don't have enough. We still haven't actually gone through everything that is in section 11.2. There's a little bit more in there that I haven't discussed, and I will not use those problems, but we will be discussing those tomorrow. And that bell said we're out of time. But I just want you to know that this is only asking you to find the sum if you get converge. And if you get converge, you're only going to get it because you're dealing with geometric. The only two tests you have right now are geometric series and test for divergence. So you're going to look at the limit as n approaches infinity of the full formula. I'm not giving you ones that you don't know how to do yet. And that homework, you don't need to write a ton down. I tried to tell you that all you need to write down, if it's the divergence test, is just this. That's all you need to do. With the geometric series, all you need to do, you don't have to tell me how you got R. Just tell me what R is. Tell me what R is, and then converge or diverge by the geometric series test. And if it's a converging geometric series, you're asked to find its sum. That's it. You don't need to show any more work than that. So you're going to love it. It's not going to take you too long. All right. Have a good day. And guess we're not going to see, but you can still come to campus, but you can't go in the classrooms, and you have to trust the school's Wi-Fi, which I will tell you, it crashed on me during second period. And I just realized that I'm actually still recording this, and I need to stop recording. And how do I stop recording?
Have a great day, Miss Blanchard.
You too.